Hey adapters, I'm Doug Parsons. I'm a partner at Simpatico Studios, where we live stream conversations about complex business and social challenges with professionals like yourself who are working on the same issues. Our shows are live streamed in front of a global audience of your professional peers on simpatico.tv. I'm building a new type of online community for professionals like yourself on the Climate Adaptation channel. If you're a regular listener of my America Adapts podcast, I think you'll find that we're taking our conversations about important problems, policies, and solutions to the next level here. And if you're interested in being a guest, we'd love to hear from you. And now join us for this latest episode. Hey adapters, today our guest is Priya Donti. She's a Ph.D. student in computer science and public policy at Carnegie Mellon University. Priya works at the intersection of machine learning, electric power systems, and climate change mitigation. She's a U.S. Department of Energy Computational Science Graduate Fellow and is also a co-founder and chair of Climate Change AI. Priya will discuss the intersection of climate change and machine learning. She also shares what this intersection means for you in practice if you are working or investing in the manufacturing, power, technology, government, or NGO sectors, and how you can collaborate with the volunteers at Climate Change AI. Hey Priya, welcome to the show.
Hi Doug, thanks for having me.
All right, so I'm checking in with all my guests. Just what's going on with COVID-19 with you? How's that affecting your PhD and the work that you're doing there?
I am so super fortunate to be able to do my research remotely at home. But of course, it is the world is really wild out there. So
It is. Well, yeah, I'm glad you're able to continue to work. Well, let's just jump right into this. And so I was trying to get my head around this episode because I thought it was really cool, climate change and machine learning. But let's start back. What are you studying there? Is that the focus of what you're studying with your PhD is machine learning?
yes, so my PhD focuses on the intersection of machine learning and electricity systems specifically. So a lot of my work is about how do we reduce greenhouse gas emissions in the electricity sector and sort of leverage the power of both machine learning and what we already know about power system physics. So like combine these two things in order to then kind of do things like forecast renewable energy, things like try to understand where we have gaps in electricity system data that where filling them would help us to, for instance, install rooftop solar power in various places. And so, yeah, that is the focus of my PhD, or at least one portion of what is a really gigantic problem.
All right, I want to step back and let's talk about machine learning. And I like to think I'm a relatively smart guy, just relatively smart. You're sitting on the bus with me and you're trying to describe machine learning to someone. And I know it's outside of just climate change too. But what is your elevator speech when it comes to what machine learning is all about? What does that mean?
So I think a lot of people get really intimidated by machine learning, but ultimately it's very simple. All machine learning is trying to do is to try to find patterns in data, usually big amounts of data, but fundamentally we're just trying to find patterns in data. And this takes a lot of different forms. There are a lot of buzzwords that you'll hear thrown around, like deep learning, which is a group of machine learning techniques that are inspired by the neural networks in our brain, or computer vision, which is when you're trying to basically analyze images and videos, or natural language processing. This is what Siri uses when you're talking to it and it's trying to understand what you're saying and respond in a logical manner. So all of these are kind of different buzzwords that you would hear thrown around for machine learning, but fundamentally you are just trying to analyze patterns in data.
All right, so and how does that apply to the climate change? And you've sort of alluded to this a little bit, but with climate change, machine learning, it's applying through electrical systems, and that's your primary focus. But what are some other areas that you can benefit in regarding climate change?
Yeah, so machine learning can actually be used in almost every area of climate change. So from climate change mitigation areas where we think about reducing greenhouse gas emissions, so things like electricity systems, buildings, industry, agriculture. We can also think about it for climate change adaptation. How can we help decision makers make better decisions by analyzing climate data, for example? And then it also has applications for policy making, for individual action, for finance. Um, and really, what it comes down to is that a lot of the questions that we ask in climate change are fundamentally data driven. And there are a lot of scientific questions that we're asking, a lot of value judgments that we're trying to make. And machine learning can basically help us analyze the data that allows us to accelerate these scientific applications that to help us make better decisions. And given that data is everywhere, there are a lot of applications of machine learning sort of everywhere in this area.
All right, so I imagine someone in your position, even outside the field of climate change, it's you want to get your hands on big chunks of data, right? It's just like that's what makes what you do effective. Where do you get your data from?
So there are a couple of different places it tends to come from. So for me personally, for example, one of the things I work on is trying to forecast solar and wind power, given that the amount of solar power produced by a solar panel, for example, varies based on the amount of sun that you have. And so in order to figure out how much solar power you're going to get in the future, you may want to use information, for example, about how much solar power was produced in the past, what was the weather like, and what is our forecast for the weather? What time of day is it? And to answer some of these questions, actually, some electricity system operators in the US actually release some of this data on their websites. So there are actually a lot of areas where data is just publicly available where you can do this kind of analysis. Um, and there is sort of another area of applications that uses satellite imagery to actually get insights that are then useful to decision makers in this area. So, for example, if you want to figure out how many buildings there are in the world or how energy efficient they are, and you don't have more targeted survey data already, then you can potentially try to find some of those answers by analyzing building outlines and building footprints in satellite imagery. So there are some kind of non-traditional sources of data that you wouldn't think of. You wouldn't think of satellite imagery as something necessarily that is climate change related, and yet that is one of the sources of data that you can use. And I kind of like this class of applications using satellite imagery to derive some kind of insight because it speaks to one of the value propositions of machine learning, which isn't just taking large amounts of data that we already know what it is and using that to drive insights, but actually taking data that we wouldn't usually use, like raw pixels in a satellite image, and actually transforming it into something like estimates of where solar panels are or estimates of where buildings are that we can actually use for climate change decision making.
All right, so many questions kind of pop in my head too. Is like there's when you're trying to influence policymakers, it's they have to have, I guess, confidence in the reliability of the data that you found, and you're like, oh, well, this is where I got it, and then it's ultimately you're almost like an artist. You're crafting something from that data that you think is going to be useful, but maybe they don't trust your judgment when it comes to like, what are you trying to tell me here? What sort of questions are you asking? Well, you're asking the wrong question. Do you encounter that a lot? Like you ultimately, are you working with other, colleagues and you're saying these are the kind of questions we should be asking? How does that work?
Yeah, so one thing I'd like to emphasize is the goal is ultimately to inform policymakers, not influence. So the idea is basically to try to help policymakers, decision makers like electricity system operators, maybe a city government, maybe an entrepreneur, try to better understand basically what are the most fruitful angles of attack for tackling climate change. And fundamentally, if a policymaker has more kind of fine grained data that they're able to collect through traditional methods. So to go back to this example of buildings, if a policymaker is able to get data where we knocked on every single door and sort of measured is there insulation in this building, is its air conditioning efficient, etc., that data would ultimately be of better quality than anything else we could get at scale, and that's what we should use to make decisions like how do I create energy efficiency policy. And so machine learning methods in this area are much more about filling gaps that where data may not be available, but where it might actually be very important to a policymaker making a decision. So for instance, if there's a whole area, a whole swath of buildings where we don't know the energy efficiency characteristics of those buildings, one might argue that having some estimate of what the energy efficiency there is, even if it's imperfect, is better than having nothing, and it at least can help make an initial decision. Now, to get to the second part of what you were saying, which is that I think I completely agree with you that if somebody is sitting behind a computer in an academic lab and is sort of coming up in their own heads with information about this is what's useful to a policymaker and that's what's useful to a policymaker, I think often that academic is going to miss the mark. And so one of the big takeaways that I and others really try to emphasize is that the kind of the problems that need to be solved and the needs that need to be addressed really have to emerge from the people who will actually be using or deploying these various innovations. So from the policymaker, from the entrepreneur, from the electricity system operator. And it's really the role of those who are working in machine learning to really listen, to really co-develop solutions alongside those practitioners in order to make sure that what's being done is actually useful and that it's actually addressing the right questions.
So I'm wondering, with COVID-19, there was this huge drop in carbon emissions because of energy use sort of train, and I'm generalizing, please correct me if I'm wrong, but emissions went flat because economic activity just collapsed for a couple months there. Is this big data that could inform some of the things that you're doing? It's this once sort of in a lifetime opportunity of like something really different happened with the electrical grid and energy use. Are you guys looking at that at all?
Yeah, so I personally am not an expert in that particular area, but I guess what I can say is there are indeed a lot of people who are trying to analyze sort of did energy usage look like before and what did energy usage look like after, and what are the sort of implications for the viability of different energy efficiency actions. So I can't really say much more about that, but it's definitely something people are thinking about.
Okay, so I guess maybe stepping back a little bit too is give us what are the strengths? And you've talked a little bit about this, but what are the strengths and I guess what are the weaknesses of machine learning? What should people be on the lookout for?
Yeah, so I think machine learning is really good at scaling human insights. So imagine, for instance, Doug, that you asked me to, if you gave me three pictures and you asked me, which picture is a dog and which picture is a cat, I could do that really easily. If you gave me a million images to do that for, I would probably get pretty annoyed with you. And so this is where a machine learning algorithm really comes into play, where this is something that I can do. I can sort of identify what makes it, or I can at a high level figure out, well, this is a cat, this is a dog, because there's some things about that that basically scream dog or scream cat to me. Um, I may not be able to write those rules down. I might not be able to say, well, a cat looks like a cat because it has ears, because dogs also have ears. And so it's one of these situations where a machine learning algorithm can likely pick up on similar kinds of things that I'm picking up on when I'm figuring out whether there's a dog or a cat, but do this at scale and sort of give some of these answers at scale. So that's really one strength of machine learning. Um, Another big one is that it's really good at optimizing very complex systems. So an example that I like to use here is our global supply chains and freight transportation systems, sort of how when, I don't know, I order a shirt online, how that shirt actually gets to my house. Um, and there are a lot of handoffs there. I mean, that shirt has to maybe go from one country to another. It has to go on a train sometimes, probably on a ship sometimes. And there are lots of things that can go wrong there. Maybe one mode of transportation can get delayed, and as a result, something misses its connection to another mode of transportation. And you have this sort of constantly changing system where you have to make adjustments. And so machine learning is good at both figuring out what's going on in that system given the appropriate data, but then actually also re-optimizing that system as appropriate in a kind of fast manner. So these are a couple of the kind of main things that's like scaling human insight and analyzing data and optimizing systems. Um, but I would say the weaknesses are that we've talked so much about data, and ultimately machine learning will not do well if you don't give it good data. There's a sort of aphorism, garbage in, garbage out, that is used to describe basically if you give a model really bad data, then it's going to make very bad decisions. And then machine learning also sort of inherits the various biases of not just its data, but the way it's designed, right? If I sit down and figure out how to design a machine learning algorithm, I may be sort of encoding some of my own assumptions about how a particular problem works, or about what I need to be doing in this scenario. And also biases associated with its use. If you use a machine learning algorithm, for example, in an existing system, for instance, if you use a machine learning algorithm to do job hiring or admissions or something, if the system within which you're using machine learning is already biased, then the machine learning algorithm is not really going to fix that for you. So this isn't really
Hmm.
a weakness as much as it is a limitation. I think a lot of people expect machine learning to bring some level of objectivity to the table, or to fix some of these underlying social issues by just putting data through an algorithm. But fundamentally, you have to deal with the social issues alongside the machine learning. It's not going to fix that for you.
All right, so I got a question from the community room here from Ken. What is the typical process like when a researcher out in the field approaches climate change AI and asks for help with a data set? Are they screened and assigned a relevant person? Is it round robin? So how you guys interact with people that way?
Sure. So maybe I should step back and talk a little bit about climate change AI as a
Yeah,
whole.
please, yes.
Yeah. So the goal of climate change AI is generally to catalyze impactful work at the intersection of climate change and machine learning. And we do this in a couple of different ways. We try to build a community working in this space. We try to kind of provide educational materials, have venues such as workshops that can sort of help people meet each other and interact with good work going on in this area. And we also try to kind of advanced discourse in this space, try to talk about, for instance, the nuances around machine learning in the application of climate change, kind of like we are doing right now. Um, and so if a researcher, if somebody in the field approaches us with a data set at the moment, we have some channels to, for example, send that like to, if for instance, the ask is to make that data set available to machine learning researchers who might want to use that data. We have some various, advertising mechanisms for that, a discussion forum and newsletter. If the goal is to really ask, well, what do I do with this data set? Is this actually useful from a climate change or machine learning perspective? Then we have a discussion forum where people can talk about these kinds of aspects. And then generally speaking, we're generally happy to, if you have a problem that doesn't fit into sort of a neat box here, where it's like, I don't know whether I would, for example, present this at a workshop or whether one of these dissemination platforms is right for me. We often tend to have one-on-one conversations with people to try to brainstorm things in this space and to try to connect people with the right other people. So there isn't like a put your data set in this repository exactly, but it's much more about the network and facilitating the network and connecting the right people to each other.
I think Ken's got some data sets he wants to reach out and give to you guys.
Yeah, please do.
All right, this might be a completely dumb question, but so you have AI, climate change AI, artificial intelligence, and then machine learning. Is it artificial intelligence and the process of being artificially intelligent, you have to go through machine learning, or is there sort of an interchangeable kind of, is there the differences? You get what I'm getting there?
Yeah, I completely understand. So machine learning is often considered to be sort of a sub area of artificial intelligence, but one that is particularly prominent at the moment. So artificial intelligence is generally the notion of trying to build a system that sort of in an automated manner makes some kind of decision. Machine learning is specifically looking at the class of approaches that where you're not encoding any rules. So I talked about the dog and cat example before. For example, if I could sit down and write down what the rules were to being a cat, like if I could say, I don't know, I don't want to offend any cat lovers out there now, but
hey, I'm a cat lover. Go on.
I like cats too, don't worry. But imagine that I could kind of distill the essence of a cat to a cat has ears, a nose, whiskers, and a tail. Imagine that sort of described everything you needed to know about a cat. And that was enough to sort of allow some kind of automated system to reason about what was a cat and what wasn't. And then that would be a rule-based system. And that is one type of system that you could create that would fall under artificial intelligence. But that wouldn't necessarily fall under machine learning. Machine learning is much more about identifying patterns when you can't really write those rules down at a really high level.
Yeah, I think the machine identifies cats look smart, and then when they see a dog, there's this sort of dumb look to their face. So you just build that into the algorithm there.
Hey, I like dogs too.
I have my biases. All right. Okay. So you guys, excuse me, but and we'll share this on the wall. There'll be a wall for this episode. But you guys did a paper tackling climate change with machine learning. And it talks about, how using machine learning with climate change. But what I find interesting is we've talked about electricity, but transportation, buildings, agriculture. I have an interest in how we adapt to climate change. In that paper, how do you, do you address those kind of topics?
Adaptation specifically?
Yeah. I guess use an example of like how machine learning is informing agriculture or forestry.
Yeah, absolutely. So I can give a couple of different examples. So let me give one in adaptation, and I guess let me give one in agriculture. So in adaptation, one of the things we think about is climate prediction. So earlier, I was sort of mentioning this idea of trying to inform, let's say, a city as to what kinds of things they can do in order to adapt to the effects of climate change that will fall upon their specific city. Now, the issue with large-scale climate models is that they're actually very, very computationally intensive to run. And so you don't tend to get answers for, or don't tend to get predictions for what the climate will be like at a certain time, or what the effect will be on a certain area. You don't get those answers at a very granular scale. You get them for a very large area. And so there's this whole area of work called that refers to downscaling climate models, trying to make them a little more spatially precise, in order to then be able to give these insights to policymakers. And there's a lot of work in this area that is not machine learning, a lot of very good work in this area that is not machine learning, but machine learning also plugs in here. And so one way you can think of approaching downscaling climate models is by just trying to make the models run more efficiently so you can run them more. And a couple of the ways that this is done is, for example, when you're trying to model clouds within a climate model, there are these really, these physical interactions that happen with clouds that are very complex to run. And that kind of add to the computational complexity of the model. And so some people, for instance, are doing work to actually, instead of running cloud physics for every single cloud, to use a machine learning model to actually approximate those cloud physics in a way that then speeds up the entire model overall. Another way people are kind of using machine learning in the loop here is to try to reduce some of the uncertainty in climate models. So for instance, ice is something that we don't know a ton about. Ice has a lot of parameters that have large effects on the climate, and we may not have precise data for like various parameters of the ice, like the reflectivity of the ice in a particular spot. And so if you can use something like satellite imagery and machine learning on that to get an estimate of the reflectivity, then you can kind of feed that in directly to your climate model, increase its accuracy, and also sort of remove all of the things that you did to try to get around the fact that you didn't have a good reflectivity estimate. So this is one example in adaptation, just trying to work on making predictions more usable by a decision maker. But there are a lot in the paper. There's some that look at, for example, trying to forecast food scarcity so that we can then adapt to that. There are applications that look at monitoring biodiversity in ecosystems so we can adapt to that. There are things that look at human migration and how can we try to understand how human migration will occur, and as a result, again, how we can kind of build social systems that are robust to that. And so kind of anywhere in adaptation where you had some kind of decision that again would be informed by data, you often can find an application of machine learning, or an application where machine learning may potentially be useful. Yeah, so I can let you ask questions on that, or I can go to agriculture.
Well, I have a few more questions here, and I got some questions in the community room. But I wanted to follow up because I'm a policy guy, and I'm always interested in the policy implications. I know you're a computer scientist, and just when I think about these different sectors that machine learning could benefit, it's always sort of like, well, they built this amazing thing, but not everyone's using it. And I think of different sectors that might not have the resources to take advantage of the use of big data and machine learning. And, and let's say agriculture, let's say big corporate firms have the money, have the budgets to sort of make big decisions that's going to influence them. And then maybe the small family farm, it's additional competition. And so I guess you need to do what you're doing. You're the computer scientist developing this, but are these sort of questions about access coming up? And who, if it's not your shop, whose is it?
So they definitely are coming up, and I would argue that it is definitely our shop. So again, I sort of mentioned earlier that any problem, any solution is not going to be well specified or able to actually have its impact if it's sort of developed in a silo. And that, I think when I said impact there, that could mean a lot of things. That could mean just carbon dioxide emissions. But fundamentally, I mean, as we're thinking about climate, we do need to be thinking about socioeconomic issues and equity and various things like that. And the only way that's going to happen is if, for example, a machine learning practitioner who wants to work in agriculture, rather than developing something in a silo and giving it to a large company, or rather than just developing something with a large company, actually goes and finds those stakeholders, finds those family farmers and says, I actually want to hear what your needs are here. I actually want to think through the climate implications of those, and I want to co-develop something with you. I think that it is sort of unhealthy and unhelpful actually for machine learning practitioners to think of this as a silo where it'll be dealt with later, because the work that we do and the questions that we choose to ask have implications for things like equity and have implications for things like climate. And so I really think the answer is that we should sort of be talking with policymakers and small family farmers and on the ground stakeholders from the get-go as we're scoping, designing, implementing everything, our projects.
And I found just my experience with PhD programs in sciences, sometimes they do have like a policy equivalent within a different school where you're collaborating and there's practicums that where like, well, it's not really your strength is doing policy, but we need to be there as a resource for you. So
yeah, I mean, and one of the programs I'm affiliated with is called Engineering and Public Policy, and this is sort of exactly what we're trying to do, where it's people who are coming in with some kind of technical background who are really fundamentally interested in answering policy questions or giving insights to decision makers. And I think through departments like that, through collaborations between pure computer science and machine learning departments and departments in schools of engineering, schools of sciences, and policymaking programs, I think that universities in some sense are really fortunate to have this cross-disciplinary conversation. But I think limiting it to within a university is still always a mistake, because fundamentally you are wanting to talk to practitioners and on the ground deployment, which may not be captured within the university community.
all right, so I think we're at the end of our episode. I want to ask you one more question, and then there's a couple additional questions from the community that we can get to in this just chatting section when we end the episode. But I guess what's next for you? I know we talked a little bit about that before we got started, but you're doing your PhD, but you get done your PhD, then what?
That is a great question, and I'll let you know when I know.
Okay.
But I think that for maybe to make that more broad, for somebody working in this area, there are a lot of different options. I mean, academia is an option. Something like working in a national lab is something that I think a lot of machine learning people or computer science people don't think about. Working at a national lab, working at a think tank, working in a government or in a policy fellowship for the government. And then, of course, a lot of people know about entrepreneurship and working for industry. But I guess there's really a wide world out there, and a lot of non-traditional paths. So, for example, there aren't, I think, a lot of people who would graduate from a PhD program in machine learning and say, maybe I'm going to do software development, or I'm going to build some kind of system, but not at a traditional tech company. Maybe there's a city government who could utilize my skills. So I think the reason I don't know is because there's sort of a lot of possibilities and a lot of them are out of the box. And I sort of hope other people consider that too if they're thinking of working in this area.
I hope you stick to the climate space. We're going to need you. So.
Oh, absolutely. That is not a question.
All right. So I want you to hold on. We're going to go into this just chatting, but this has been fabulous. I learned a ton, and thanks for coming on.
Thanks so much for having me, Doug.
All right. Just one sec.